Okay, we talked about covalent bonds and how the whole figuring out the Lewis dot diagram, Lewis structures have to do with giving everybody a complete octet. Electrons except for hydrogen. So, this is one of the theories, one of the beginning theories of bonding. So there are some exceptions. Of course, there's an exception to every rule. And here are some exceptions. Here are some exceptions. There we go. Incomplete octets. So here we have BEH2. What's wrong with that? According to the octet.
Well, H can't have.
Well, H only gets 2,
Yeah.
and it has 2. Beryllium only has 4. But if you look at beryllium, how many valence electrons does it have? 2, and hydrogen has 1. So they have 4 electrons. So this is an exception to the octet rule. BEH2 is perfectly happy existing that way. BF3, boron trifluoride, same thing. It only has, boron only has 6 electrons around it. It's perfectly happy that way. So there's a couple of exceptions. If you have an odd number of electrons, NO2, the oxygen has 6, there's 2 oxygens, that's 12 electrons. Nitrogen has 5, so 12 and 5 is 17. Well, you can't have complete pairs. The 17, P doesn't go into 17 an even number of times. So you end up with a single electron on the nitrogen. Those are known sometimes as free radicals, or just radicals. Okay, compounds that are radicals are highly reactive, and sometimes they're generated in our body, and they can do damage. They can cause chromosomal damage, cancer, and that's why you see people take supplements to scavenge free radicals in your body. And they can be caused by a number of things you ingest, environmental things, sunlight can cause free radicals.
How about your point that a minute ago?
Christmas music? Bing Crosby. Oh.
What? You cannot not like Bing Crosby.
I like Bing Crosby. I'm surprised you even knew about Bing Crosby. You're way too young to know about Bing Crosby.
Oh, Bing's great. The Rat Pack are cool too.
You know about the Rat Pack?
Yeah.
I don't know. Did you get lost in somebody's attic sometime? I mean, I don't know.
Yeah, but
What happened there?
locked me up there.
Okay. So if you look at ClO2, how many valence electrons are we dealing with? 19. So if we do the Lewis dot rules we wrote, so there's chlorine, we give each oxygen an octet, so we've used 16. I got 3 left over. Where do you have to go?
Chlorine.
And a chlorine. So we got 1 pair and boom, 1 electron sitting there all by itself. So that's a radical.
Just form another pair out there.
Form another what?
I was gonna ask.
They're just happy. So that's the way it exists. Expanded octets. When we get down to the third row, the three levels, there will be 3 s, 3 p. There is 3 d orbitals there. They may not be occupied, but they're there. But it turns out we could use those, which are there, so we can form compounds like SF6. So sulfur here has how many electrons are on it? No, you gotta count each line as 2. 12 electrons. So sulfur has 12 electrons. So they call it an expanded octet. Now later on, there's other theories that address these anomalies that we're going to look at. So this is like the first one in the theories. So boron triiodide, arsenic pentafluoride, and xenon hexafluoride. So those are the skeletal structures. Boron triiodide has how many valence electrons? Sorry, how many? No. If we're doing the structure, that's the skeleton. Boron triiodide has how many valence electrons? Bi3. 24.
Is that right? Yeah.
I don't know.
7 times 3.
7 times 3 for the iodine, that's 21, and boron has 3, 24. I knew you were right, but I wanted you to. So the next step is to do what? Octet. How many have we used? We've used all 24. So we're done. Was boron happy? No. And we can't form a double bond. So that's what Bi3 looks like.
Wait, hold on. You lost me when you said he's not happy. So,
Boron only has 6 around it.
right.
But it turns out this is an exception, so it's perfectly happy this way. If you were to look at it by the rules of octet, you'd say it's not.
Okay.
And when we go on to the next theory of bonding, you're going to see how this actually works. So if we look at the next one, arsenic pentafluoride, how many valence electrons are we dealing with?
37.
Oh, you're ahead of me. 37. I'll take your word for it. 37?
No, 38.
38? Fluorine is 5 times 7 is 35.
And then AS is 3, so 38.
38.
35. Right?
We get 38? Everybody okay with 38?
Yeah, F is 7, 7 times 5 is 35. AS is 3, so 3 plus 3 is 38.
Can I get the right number? So how many have I used? I've used 40, haven't
Yeah, 8 times 5. So, 40. We've used too much.
I? AS is in what column?
You're confusing me, oh my goodness.
Arsenic is in 5.
It's 5.
So it has 5 valence electrons.
Why was all of that 3 minus?
40 electrons. 40 total valence electrons. I don't know what you would have came up with 3.
I was looking at 3 minus.
Okay. It gets a charge of 3 minus, but it has 5 valence electrons.
Yeah.
So I know I'm right.
I know. Well, you
That's
thought
why I'm
it was
standing
37.
here. That's why I'm standing here. Okay. So I've used up all 40. I have no more. So we're done with that one. So that's what that one looks like. Xenon tetrafluoride. How many valence electrons?
I'm not answering this time. Wait.
You are, but you're not answering correctly. Okay.
8 and
I know we got this higher math here.
We got this.
He's right. He was right. 36.
No, I mean.
Oh,
Yeah, we were like, I was saying like the same answer.
Oh, I thought you were saying
No,
back
no.
off, but yeah, we got, oh, I see what you're saying.
Yeah, I'm sorry, my voice doesn't change.
It's a generational thing, because I'm still thinking about how you knew Bing Crosby, and you're going on to other things. Okay. So we have 38. Right?
Yeah.
4 fluorines, that's 28, and then 8 for xenon. Oh, 36.
Yeah,
36. Okay. 1, 2, 3, 4,
I did
5.
read it all.
Give each fluorine a complete octet. Well, I can't wait to hear this on the recording. All right. How many have we used? 32. So how many got left over? We're supposed to have, we got 4 left over. What do we do with them?
Put around the,
Put them around the xenon. 2 here, 2 here.
but it doesn't matter where you put those dots, as long as it's around.
Yeah, it's got to be on the xenon. And that's what it looks like.
So I use the clockwise rule in xenon for the central electron.
The clockwise rule.
Or counterclockwise where you put a dot on each side.
Because when you, oh, I see what you're saying. They line up in pairs in this case.
Remind me again, for my brain, why you, which one goes in the middle? How do you decide?
The least electronegative. So those are exceptions to the octet rule. Okay, and where are we going here? So now we're going to go talk about bond enthalpy. What's with bond enthalpy? We can tell something about the stability of a molecule by its bond enthalpy, which is the enthalpy, the energy needed with breaking a particular bond in 1 mole of a gaseous molecule. So if we look here, we have hydrogen, chlorine, and nitrogen. So if you look at the bond enthalpies, hydrogen takes 436.4. Chlorine, 242. Why does it take less energy to break the chlorine-chlorine bond rather than the hydrogen-hydrogen bond? Well, if you think about this, what forms a bond? It's sharing electrons, but here you have an atom and its nucleus, and this, let's say, it's its valence electron. Here we have another atom, valence electron, and its nucleus. What actually happens is this nucleus attracts the electron from the opposite atom, and this nucleus attracts the other electron. So it attracts the opposite, brings them together and shares. So to break apart hydrogen, it takes more energy to break apart chlorine. Why? Who's closer? All right, remember, the atomic radii of hydrogen is smaller than chlorine. So the nucleus of the hydrogen to the valence electron of the other hydrogen is closer than if I had chlorine. This distance is a lot farther. So the farther, what is the attractive force as we get farther away? Less. So to pull them apart takes less energy. It's easier. All right? So you see, if you go to HCl, now we got one that's big and one that's small. It should take more energy than the Cl2 and less energy than the H2. It's certain. It does. It's more energy than the Cl2, and it's slightly less energy than the H2. Look at nitrogen. Nitrogen is over 2 times the amount. Why? Think about the Lewis structure for nitrogen.
This?
This is hydrogen. This is chlorine. This is hydrogen chloride. Oh, then we have nitrogen. We said how many valence electrons in nitrogen? Quick. No, N2. Molecule 10. Well, if you do the Lewis structure, you end up with, what do we got with nitrogen? A triple bond. Okay. Triple bond. And what do we say about multiple bonds? A triple bond is stronger. It's harder to break. Is this harder to break? Yes. Okay. So hopefully this is all starting to conceptually come together for you as to why things react the way they do. She's asking you who Bing Crosby is. The other day in class I said, well, there's hope. There's not hope, it's Crosby. And nobody got it. Bing Hope. Bing Crosby is Bob Hope. Was Bob Hope, and that's very old. Okay. So.
Did Bob Hope just die?
No, he did that very well.
No.
Well, he still did, but.
Working on the street.
Yes. Okay. Now, if you do about polyatomic molecules, not diatomic, it gets a little bit more complicated because you got multiple bonds breaking. So they talk about the average bond enthalpy. So we can calculate the enthalpy of reaction by the sum of the bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. In other words, the energy to break the bonds minus the energy released by bond formation. Remember the law of conservation of energy, if I put energy in to break the bonds, when I form new bonds, I release energy. Really, chemistry just boils down to, I have these molecules, I'm going to break them apart into the individual atoms, and then come over here and reassemble them differently. So I have to spend so much energy to break them apart, but I'm going to get some energy when I put them back together. And the difference between those, though, is the energy of the reaction, the enthalpy of the reaction. That's all it is. So here's a table, it's in your book 8.6, bond enthalpy. So it tells you, to break a hydrogen-hydrogen bond, it's 436.4 kilojoules per mole. Carbon-bromine bond is 276. It tells you the energies to break all these bonds.
They're reason they're different colors.
Is there a reason there's different colors? I'm sure there is, but I don't have the faintest idea what they are. I think they're that colors because they're probably the most common ones you're going to find.
Oh wait, hold on. Diatomic.
Oh, diatomic molecules. So, and there's some more. So if I look at this reaction, hydrogen plus chlorine to give me hydrogen chloride. First thing I have to do is take the reactant molecules, the hydrogen and the chlorine, break them apart. So now I got hydrogen atoms and chlorine atoms. And when I put them together to give me hydrogen chloride, I release energy. Well, it turns out, after everything is calculated, the delta H is negative 184.7 kilojoules per mole. This reaction, I'm taking ammonia, breaking it apart into nitrogen and hydrogen. So I got to take the ammonia molecules, rip them apart into nitrogen atoms and hydrogen atoms, then reassemble them into hydrogen molecules and nitrogen molecules. I do all the calculations, it turns out delta H is 92.6 kilojoules per mole. What can you tell me about these two reactions? Exactly. One's exothermic, one's endothermic. The negative delta H tells me if I take hydrogen and chlorine, I'm going to make hydrogen chloride, I'm going to release heat. If I want to take ammonia and break it apart into nitrogen and hydrogen, make nitrogen and hydrogen, I have to put in energy, a net amount of energy. It may be a good thing to know that one of these is going to happen. Last thing I want to do is mix two things together and find out I have a very exothermic reaction. It tends to go boom. I don't want to be standing there when it does. Otherwise, I'll be joining Bob Hope and Bing Crosby. Okay. So here we have combustion of methane. By the way, for the labs, if you did the calories of foods, when they asked for the products of combustion, every single equation we've ever done is always carbon dioxide and water. So what we do with methane is there's CH4, we're breaking 4 CH bonds. For oxygen, we're breaking 2 oxygen-oxygen double bonds. We're forming 2 carbon-oxygen double bonds. And we're forming 4 oxygen-hydrogen single bonds. So we know what pieces we're taking apart, we know how we're putting them together. So you go to that table, and break apart a carbon-hydrogen bond is 414 kilojoules per mole, so we have 4 of those. To break up the oxygen-oxygen double bonds is 498.7, we had 2 of those. So that's how much energy we have to put in. What do we get out? Well, we form 2 carbon-oxygen double bonds, each at 799 kilojoules per mole, and we form 4 oxygen-hydrogen bonds. So if you do the math, we end up with a delta H of negative 785 kilojoules per mole. Does that sound right? I don't see yes because it's up on the slide. What were we doing? Burning methane. Where do we burn methane? What? Yeah. Natural gas furnace. So if you have gas heat in your house, it's not propane. You don't have a propane tank. It's piped in from the city. It's natural gas. That's methane. Why do you have a methane furnace? Why do you have a furnace? You want to be warm. So the furnace gives off, there it is. In fact, it gives off 785 kilojoules for every mole of methane that you burn. Except if you look at your furnace, it won't say that. It'll say BTU, which is a British thermal unit, which is some archaic unit that they use in heating and air conditioning. Oh, and that ended that.